Hello. Yeah, in this video, let's continue our series of machine learning using R. And today's topic is how to perform nonlinear PCA for dimensionality reduction. The PCA stands for Principal Component Analysis. As you know, it is a dimensionality reduction technique to reduce high-dimensional data into their principal components. The principal components are actually linear combinations of the original variables. So the nonlinear PCA is the principal components may be nonlinear function of the original variable. Okay, so the package we need is a kernlab. Let's load that, and also ggplot2 for graphing. Set random seed, sample size 300. Calculate two variables t and h, and then create x1, z1, z2. And then we build 10 observed variables as nonlinear noisy functions of z1, z2, and h. Okay, so we actually have created a high-dimensional data set with 10 variables, but they are actually functions of z1 and z2. Okay. And so this data set, it's 300 rows and 10 columns. And this is what it look like. So now we need to perform kernel PCA to reduce the dimensionality. Okay, so first, before you can do anything, you need to scale the features. So use the function scale. So you get scale them to mean 0 and standard deviation 1. Okay. Then you can perform kernel PCA with RBF kernel and keep 2 components. Okay. So the command you can use is use the function kPCA and the data equal to. So here this is important. You have to feed this data equal to you have to feed it a data frame. So the x underscore scale is actually a data matrix. So here you have use s dot data dot frame x scale, and kernel equal to rbf dot. So that's the option for using the rbf kernel, and k parameter you're going to list equal to sigma equal to 0.2 and features equal to 2. So we're forcing this kernel PCA to use 2 features. Okay, it takes very little time for it to complete. So now we are looking at 2D embedding of the training data. So let's do the kPCA as data frame. We use a predict. Okay. The kPCA model and x as data frame x scaled, and column them into PC1 and PC2. So we're extracting the principal component 1 and 2. Okay. And now we need to evaluate what we have done. So we first just want to show you the dimensionality reduction. Okay, so the original versus reduced dimensionality. So the number of column for the original data x scaled is 10. So we had 10 variables, but the number of kernel PCA is 2. We got 2 features there. Of course, this is just a sample data set. It also works if you have like 100 variables. You can reduce them into 2. And also in this example, we also generate the data so that all the 10 variables are a function of the 2 underlying variables. Okay, so everything works out nicely. Eigenvalues, these are importance of each component. So we can extract the eigenvalues by using the function EIG from the kPCA model. I can print them out. So these are the eigenvalues. And then from the eigenvalues, we can calculate the proportion of variance for each of the eigenvalues. And then we can also print out the cumulative proportional variance. So you can see the first component explain about 57% variance. Adding the second component, then they explain all the variance. So there's nothing to explain after component 1, component 2. So we got missing data there. Okay. We can visualize the 2D embedding. So we can use the ggplot. So we're using this data set, and we can say this x is PC1, x2 is PC2, and the geo point alpha equal to 0.6, put in the theme minimal and label it as title Kernel PCA on 10 variables of nonlinear data. Okay. So it shows up as on the right hand side. Okay. So this is the data points in the original data set, which is projected into this 2D embedding the PC1 by PC2 coordinate system here. Okay. Of course, you can do some additional work. For example, you can do clustering of these data points. But this is the clustering within this PC1 by PC2 space. Yeah, I checked. Unfortunately, the distance or the order of closeness of points in this PC1 by PC2 and those in the original 10-dimensional space, they're not preserved. So meaning if you do cluster analysis in this reduced space, the cluster you got are not actually applicable to the cluster back in the original data space. Okay, so just additional note. Okay, so this is just a quick example showing you how to perform the kernel PCA for nonlinear principal component analysis to reduce dimensionality. Thanks for watching.